and present this material to you. And I hope that it will be relevant. Reforecast data is something that we have created partly with the needs of hydrologists in mind. And we have a reforecast data set that corresponds to NOAA's current operational global ensemble forecast system. And I'd like to tell you about that today. I'm a scientist from the NOAA Earth System Research Lab, Physical Sciences Division, located in Boulder, Colorado. Let's see. So what I'll be covering here first is just a quick motivation for the reforecast data set and a description of what specifically we have created. And then I'll spend some time talking about how you can actually access this reforecast data set. We've tried to set up both a web-based and FTP interface that should be relatively convenient for you to get access to this data. After that, I'll talk about the performance of the modeling system that was used over that period of time where we conducted the reforecasts, and then give some examples of our post-processing method and some real-time experimental products that we have generated using these reforecasts. So as motivation here, presumably you're very well aware of the fact that our weather forecast models have systematic errors. So for example, if we were looking at a time series of temperature forecasts here, and this is 14-day forecasts on a series of dates, it's possible you might see a synthetic time series that looks like this synthetic one that I've created here, which shows that the mean forecasts are biased, more typically warmer than analyzed conditions. Another deficiency that's common in ensemble prediction systems, and ours is certainly one that has this problem to differing extents for different variables, is that they're underspread. The range of simulations often doesn't encompass the actual conditions that occur here. And so with post-processing, we hope to be able to correct for some systematic deficiencies like these. Now, another motivation for doing a very long set of retrospective forecasts is that for actual events, it certainly helps to have a large training sample size. So let's say that our recent time series of past observations and forecasts are like the one that's shown here. And today's forecast looks nothing like what we have had over the past 45 days. Well, as you would expect, what you would really like are forecasts similar to today's forecast in order to make a statistical correction to today's forecast. So you'd like a decent sample size of similar events, and that may mean you may have to go back several years, maybe even decades, to populate that with a number of samples that are similar. Now, similarly, for hydrologists, I think you would like to have you care about these extreme sorts of events, so you would like to validate your models on lots of cases with these more extreme precipitation events also. So these reforecasts, as I have taken calling them, some call them hindcasts, are numerical simulations of the past weather using, to the extent possible, the same forecast model and the simulation system that's used operationally. I like to call them reforecasts to make a distinction or a connection in the mind of folks with reanalyses, because a reanalysis is there to leverage a modern data simulation system and apply it to observations in the past to develop a climate record of past analyses. And that really is a necessary first step for doing a reforecast and getting a reasonable result. So think reanalysis and reforecast together. Here is some details on the reforecast data set that we created. First of all, this is a V2 because we have a V1 reforecast data set, which was done with a 1998 version of the model, but now it's that data set has grown increasingly irrelevant as operational models have increased in sophistication and resolution. So this one was done with the NCEP Global Ensemble Forecast System that was made up another half year to year. And every day, once daily at 0Z, we produce an 11-member ensemble forecast, which consists of a control, temperature members, and we have done this every day from 1984 through current. For the most recent forecasts, we're just plucking 11 members from the operational global ensemble forecast system. Our 11 members leverage in the past the climate forecast system reanalysis, the CFSR initial conditions, and then a set of perturbations which mimic what NCEP does operationally. It uses a technique called ETR, or the ensemble transform with rescaling. Now, in the new operational ensembles, they actually are using a somewhat improved system for defining the initial condition, which is a hybrid ensemble common filter 3D bar analysis scheme that we helped develop. The resolution of the system is T254, that's global wave number 254, so it can resolve 254 sinusoidal variations around a given latitude circle. And that ends up being roughly equivalent to a 47-kilometer grid spacing with the associated grid, Gaussian grid that's used here. Now, it's only conducted at that resolution out to day 8. After day 8, it switches to T190 42 levels, which is about 70 kilometers. We maintain what we call a fast data archive, meaning a spinning disk archive of 99 different variables, 8 of which we store at the original half-degree resolution and the rest at 1 degree. We also keep the mean and the spread if you would prefer to not have to access all of the individual ensemble members. We have another archive, which is the full data set, which we keep on tape at the U.S. Department of Energy Lawrence Berkeley lab, and I'll share the hyperlink to that site in coming slides. Okay, so how do you access this data? We set up a number of ways of accessing it. I guess first of all, let me share with you what data is saved. And here, looking at both mandatory levels and select signal levels that are down near the ground, you can see the information that we have stored: winds, UV, temperature, geopotential, and then for the mandatory levels below 300 millibars, specific humidity as well. And then a number of vertical levels down the surface that we put out there with wind energy applications in mind. And then there are special variables, and we've tried to take into account the needs of hydrologists and these extra variables. So they include things like 2-meter temperature, specific humidity, 10-meter winds, the precipitation amount, runoff, and fluxes of latent and sensible and ground, so surface fluxes, as well as radiative fluxes there. So hopefully this is enough data to facilitate you doing the sort of things that you need to do in hydrologic applications. We have set up a website here, and the hyperlink is shown at the top, that allows you to point and click your way towards subsets of data. And this is, I think, the website that you would want to go to if, first of all, you're familiar with the NetCDF data format. And if you need a moderate amount of data, meaning let's say that you need data covering a relatively limited geographic region, say a European country or a basin within that country. In that case, the data that you would be fed back would be megabytes to a few gigabytes, and our system is capable of handling that sort of processing for you. And this interface would allow you to pick out particular variables that you might want, such as total precipitation, a range of dates, forecast hours. And though I'm not showing you here on this slide, this form continues and asks you for other aspects like what geographic region do you want. You can draw a lat-long box, or you can use a predefined region like a box covering Europe. It's also straightforward to get FTP access. There's the link ftp.cdc.noaa.gov. You call yourself anonymous for the user, and then you provide your email address for your password. And CD to projects, Reforecast 2. And then underneath of that, the data is organized by year, then by year and month, then by year, month, day, hour. So for example, for the first day of 2000, you'd CD to 2000, then 2001, then 2001, 01, 00. And if you did that and listed the contents, here's what you would see. And this is going to be the same for every day. We have archive the control forecast and then these perturbed, so that's C00 and P01 to P10. And then we have separate subdirectories for the mean, ensemble mean condition, and spread. And if you were to go into one of those, let's go into the control directory, you'll see that there are two subdirectories, Gaussian and lat-long. The Gaussian is for the select set of 28 different fields that we thought were most important to have available on the original Gaussian grid. And then the lat-long has got those variables plus all the rest on the lat-long. So let's CD to that lat-long. And if you list the contents, I'm just showing you the first couple entries here. But you see files like a PCP surface, and then the date, and then C00 for the member number, and then .grib2, .grib2.inv, and such. So what are these various files here? First of all, I've highlighted here two files, which are first of all the first week's forecasts, and then the second week's forecast, that T_T190 file, which is after we switched resolutions in the second week to the lower resolution. These files are for accumulated precipitation at the surface, and hopefully we've given the file names variable, or we've listed the file names such that you can kind of understand what the contents are. So there's CAPE, convective available potential energy, SIN, which is convective inhibition, and so forth as you would look through this directory. Okay. If you happen to be using a method of accessing the data that can leverage inventory files, we've also set up inventory files that can be used with wgrib2 or with Python, and that's the .inv files and the .pydx files. And if you use those, you'll get much faster loading of the data. If not, then the first thing that you do when you start accessing a lot of Grib files is you start building these inventory files on the fly. Okay, going on, a few characteristics of the raw reforecasts. You may have seen figures like this from the European Center with their ERA interim, the reforecasts initialized off ERA interim. Here I'm showing you a time series of yearly average skill for 3, 5, and 7-day forecasts, both from version 2, which are the lines without the color filling, and then version 1 reforecast. That's that old 1998 reforecast data set that we created. And take a look at sort of in the middle there. The unfilled red lines are higher than the filled blue lines. So that's saying the big 5 forecasts are as skillful as the old 3-day forecasts, or even more skillful in recent history here. And you can see some non-stationarity. The forecasts are worse in the distant past than they are in the recent past. And if you were to look at other aspects, so let's say, for example, tropical cyclone tracks, you'd see more non-stationarity. The tropics are showing more of this decreased skill at times in the distant past relative to more current times. Okay, so let's go on. This is just a slide that I threw in from recent work that I did trying to demonstrate characteristics of the MJ or Madden-Julian oscillation, which is a phenomenon that is responsible for a lot of tropical precipitation variability. And while I was doing that, I was interested in what are the biases in precipitation in this data set. And you can see here that relative to this global GPCP precipitation climatology data set, our reforecast tends to be too rainy, and especially in the first days of the forecast. So that's one of those systematic errors that is nice to know about and that potentially can be adjusted in subsequent forecasts and through a process of statistical adjustment of the real-time forecasts. So let's talk about that now. Here is a technique that we have been applying for a while. I'm not saying that this is the best post-processing technique, but it certainly is simple to understand. And this is a slide that I put together with our old first-generation reforecasts. So consider, first of all, the picture off on the left-hand side. Let's say that our 24 to 48-hour forecast in the limited geographic region. If you're not familiar, this is the Northwest U.S., a couple states in the Northwest U.S. Well, the forecast, ensemble mean forecast, looks like that panel on the left. And then just to the right of that are the observed conditions or the analyzed precipitation associated with that a couple days later. Well, there could be systematic biases. The forecast could be too wet, as well as potential detail related to the mountainous terrain out there in that region that could be picked up, and you can apply some statistical downscaling. So what we have done is basically to take the grid points in this region and go back into our past forecasts and find dates in the past where that precipitation pattern looks like today's precipitation pattern. So, for example, in that box on the red, highlighted with the red, on the left-hand side is a pattern that looks relatively similar to today's forecast. Now, the real key data is the analyzed conditions that were associated with that, and that's in that black box. And you can see that if we go and we find past forecasts, which have a pattern match with today's forecasts, and then we have the observed conditions that go along with that, then we have the potential of making an ensemble of analyzed conditions from which we could make probabilistic forecasts. So let's actually verify those probabilistic forecasts, and that's on the next slide. And this is data over many years, several decades worth of data, and over a set of grid points that covers the contiguous United States. Our forecasts are very reliable. When we issue a forecast probability of 95%, it tends to happen 95% of the time, at least for everything but the most extreme precipitation forecast events. If you were to look at, let's say, 50 millimeters, it wouldn't be quite as reliable, but it would still be very reliable. So you can see it's reliable at the first day, from days 2 to 3, days 4 to 5. So this is one method. You could apply another that would allow you to leverage this reforecast data set to provide reliable precipitation forecast input guidance into hydrologic systems. This is just a comparison here of our version 2 and our version 1 reforecasts. On the left are Breyer skill scores for the greater than 2.5 millimeters, and then on the right, greater than 25. The solid lines are the skills at different lead times for our second generation reforecast, and then the dashed lines are for our first generation reforecast. And just a couple of characteristics to go over here. You notice a change in skill here again over the United States as a function of the month of the year. That's the x-axis from January, February on through December. And that skill is lessened. This is after post-processing now. It's lessened in the summertime. And that's just the nature of the storms that are producing the precipitation change from wintertime being more mid-latitude extratropical cyclones to in the summer being more related to small-scale thunderstorms, which are harder to predict. Another characteristic is that the post-process forecast guidance is significantly better in the second generation than in the first generation. Our day 2 forecasts are comparable to the old day 1 forecasts, for example. And in fact, as you get out towards, let's say, day 5 to 6, it's more like a gain in lead time of about a day and a half. You can also see that the skill goes down for the 25 millimeter event relative to 2.5. It's harder to get the details of that heavier precipitation forecast quite as well as with the lighter precipitation amounts. And that's generally because they cover a much smaller area of the globe, so small position errors matter a lot. We maintain a web-based set of products, regrettably only covering the United States, but we apply our analog technique in real time, and we produce lots of plots for various thresholds and various lead times. Here's just a recurrent example showing you the 5 to 10 day forecast probability of precipitation greater than 25 millimeters after we've calibrated it with an analog procedure. And this is relatively current, and then the hyperlink there is shown at the bottom for you if you were interested to go and look at other forecast products. And these are available in real time. Here's a slightly different way of presenting the data. This is the probability of the precipitation exceeding the 90th percentile of the analyzed precipitation's distribution. And so precipitation here may be much lighter in the western United States, where it's relatively dry, than in the eastern United States. But it's giving you a sense of how much of an anomaly is it relative to its climatology. And you can see that for the next couple of days, starting tomorrow evening, the Los Angeles area of California was expected to have a lot of precipitation, as well as the Salt Lake City area. We also have temperature forecasts that are post-processed. Just showing you an example of our probabilities of temperature being either in the upper or lower tercile, shown on the left, and as well as the Ensemble mean anomaly. And following ECMWF's lead, we also produce a graphic called the Extreme Forecast Index. To save time, I won't go into the details of this, but this is measuring the forecast today relative to the model forecast climatology for temperatures, that's the colors, for precipitation in the green shading, and for winds in the purple. So it gives you a sense of how extreme is the forecast relative to its own model climatology. And very recently, we've put online some tornado probability forecasts. This is an extremely rare event, of course, tornadoes. So this is the sort of thing that we thought a reforecast data set could be particularly helpful for. And it's an analog procedure, again, that leverages the fact that tornadoes are related to vertical wind shear and instability in the atmosphere. And we go and we look for past analogs to today's forecasts for those variables, and then use the observed tornado conditions on the dates of those similar analogs in the past to form these probabilities. Okay, to change significantly here, another thing that I'm thinking that some of you might be interested in doing is running some regional reforecasts of your own with a higher resolution limited area model. One of these, at least used commonly in the United States, is WRF, W-R-F, the Weather Research and Forecast Model, that is supported by NCAR, the National Center for Atmospheric Research here. And it's got a lot of users, I presume, in Europe as well as throughout the world. And we maintain a special tape archive that contains not just mandatory level data, but all of the vertical levels. Basically the entire data set that we create with all of the information. And this is just a screen capture showing you the hyperlink there up top and then what the screen looks like when you log into that web link there. So if you have a particular case that you want, you can enter that case date and either get the control forecast or select perturbations. And you enter your email address and it comes back when that file is ready for you. And you'll be provided with a very large Grib file which contains all of the forecast data that you need. That can then provide an initial condition and or lateral boundary conditions for a regional simulation. Just some notes here that we won't go over that you might find helpful if you did try to apply the WRF system using our data. Okay, so in conclusion here, our data set has been created and it's consistent with the current operational version of the NCEP Global Ensemble Forecast System. It's easy to download, that data is free to you, and even as NCEP changes their model in the near future, we're expecting to maintain this frozen version of the model for several more years until at least we get another reforecast data set in place. As I've shown you, it improves precipitation forecasts by providing a large sample of past events to support statistical post-processing, and it can be useful for other applications, for regional reforecast initialization, or diagnosing problems in a forecast model that can potentially only be teased out with large sample sizes. And of course, I hope that it might be useful to some of you HEPEX participants here. Finally, if you are looking for a journal article that describes a little more in depth what we did, there's the information for you right there. So thank you very much for your attention, and I'm very happy to take questions.
Okay, thank you very much, Tom, for a very interesting talk. Very useful stuff indeed. I will ask people from the audience now to give questions. So if you have any questions, please unmute yourself and pose the question.
Tom?
I am still here.
Yeah, this is Satish. Just have a quick question. I think you might have mentioned, but missed it. So you said you are providing, you have reforecast and as well as post-processor reforecast. So is it possible to get, like if somebody calibrated the hydrologic forecasting system using the post-processor reforecast, and if they want to use the post-processor, is it possible to obtain a post-processor forecast in real time as well?
Well, we have those web-based products available over the United States, and within NOAA, we also supply Grib data sets of our probabilities. It would be possible for me to also share the code that I apply so that if you wanted to run this with your own data over somewhere outside of the US, you could do so.
Oh, okay, thank you.
Do we have any further questions? You can also send them to the chat if you cannot use your microphone.
Hello, Michael here. Can you hear me?
Yes, I hear you.
Also like to say thank you very much. Just a quick question about the spread. What do you mean by the spread? We've been discussing how to talk about spreads when we have 5 and 10 ensemble members. What do you guys use?
I'm not sure if I fully understood. So the question about what do we use to calculate the spread?
Yeah, how do you calculate it, I guess? Is it the minimum and the maximum, or is it something else? Or?
Oh, it's just simply the sample standard deviation about the ensemble mean.
Okay. Yes. Thanks.
Mm-hmm.
Tom, I have another question here as well from your talk. You mentioned you're using analog forecasts as a sort of a bias correction. What other methods are you using as well? Can you just elaborate a bit on that?
Oh, we've tried logistic regression. There's a paper that I did with Jeff Whitaker in 2006 that went over kind of the strengths and weaknesses of the analog approach relative to logistic regression. So that's one that we have tried very commonly. I also was joined recently by Michael Scheurer, who came from the University of Heidelberg and is working with us on applying his methods, which have underlying them a distribution fitting approach. And I think that may end up being better than the analog approach for especially high precipitation events. So we are considering rejiggering our real-time web graphics to use his approach in the future, pending some more successful validations. But if you just Google Michael Scheurer, Scheurer, you can get to his web page and find some of his recent articles that describe his methods. And again, they're basically a flavor of distribution fitting.
Okay, thank you. Do we have any more questions? Otherwise, I'm sure Tom will be happy to take any questions through email after this talk. So if there are no more questions now, I thank Tom again for this talk and hope that you all use the reforecast as much as possible. And the next seminar in this series will be on the 26th of March, and then the talk will be on using standardized precipitation indexes globally for drought. So I'll welcome you back and I'll post more information on that as soon as possible. So thanks again, Tom, and thank you for listening.
You're welcome. Thank you.